In this video, we're going to be working see homework 9.1. We're going to be computing integrals that have products in the integrand, doing a lot of UDV. That's kind of the new thing for us. Okay, but we'll also do some UDU and some old-fashioned integrals that have product where we like algebraic simplification. Okay, so the first few is just like use integration by parts. I'm telling you, it's UDV. So, different sheet of paper and all right, number one. Integral of x e to the x dx. Okay, I'm thinking to myself, I late. Okay, I've got an algebraic function and an exponential function, so I need to let algebra be u and exponential be dv. So u equals x, dv equals e to the x dx. I need to take the derivative of u and the antiderivative of dv. Okay, then I'm going to need to remember the important formula, is going to be that the integral of u dv equals u times v minus the integral of v du. And then I'm going to plug in all the pieces. The integral of x e to the x dx is going to equal u times v x e to the x minus the antiderivative of v du. And we know an antiderivative for e to the x dx, that's going to be x. Number 2 is going to be x cosine of 2x. I late got an algebraic function and a trigonometric function. So u equals x and dv equals cosine of 2x dx. We're going to take the derivative of u and the antiderivative of v. I'm going to copy the formula. And under here, I'm going to say that's going to be equal to u times v. 1/2 x sine 2x minus the antiderivative of v is 1/2 sine of 2x. du is dx. That's not useful. Okay, so there we go. And then we can anti-differentiate that. Okay, we're going to divide another 2 to prepare for the chain rule. The antiderivative of sine would be negative cosine, so I'd have plus 1/4 cosine of 2x, and then add my plus c. 3 x squared natural log x. And might be a little bit different from the other two. Thinking I late a log and an algebraic function, u and dv. U is going to equal x. No. U is the log. And in the habit of u being a power of x, which, in AP calculus it usually is, but not always, as we can see. So u is going to be natural log x, dv is going to be x squared dx. And du is going to be 1 over x dx. All right, copying the formula. And so it's going to be uv 1/3 x to the 3rd natural log x minus the antiderivative of v du. So 1/3 x to the 3rd times 1 over x dx. Okay, I'll do it this time, but I would like to just be able to write 1/3 x squared. See that coming, because we'll see a couple more of these, and we saw one of the examples in the lesson where we had power of x times natural log x, and this is always going to happen here. So 1/3 x to the 3 natural log x minus the integral of 1/3 x to the 2. Okay, and when we do that, we're going to add 1 to the power, divide by the new power, add our c, and that will stay the same. Okay. Right, number 4 is 2x secant squared x. I late 2x is algebraic, secant squared x is trigonometric. Also, I'd much rather take the antiderivative of secant squared x than the derivative of it, but that's a different discussion. So I'm going to let u equal 2x and dv equals secant squared x dx. That means v is tangent x and du is 2dx. I know that you're getting to the point where you know it, but if you really want to solidify that, you're going to copy it down every time. Integral of u dv equals u times v minus the integral of v du. And so that's going to be uv 2x tangent x minus the integral of v tangent x du is 2dx. Okay. And this one, right here, this antiderivative of tangent x, I'm going to say, at least for now, that it's going to be all right, especially today, to just look that up. It might be something we think about doing, in the next lesson. How do we compute that antiderivative? It's really something you could have done last semester. You could use U-substitution. I'm going to just say this is minus 2 natural log absolute value of cosine x plus c. Now, if you're interested in why that's the case, there it is. You do U-substitution, rewrite tangent as sine over cosine, and that's kind of where you get the natural log of cosine x from. I'll just move on. The next one is x squared sine x dx, and I'll tell you, this one's going to require 2 iterations. So I'm going to do it kind of the old way, but then I'll also do a table or a chart off to the side. So I late algebra before trigonometry. I'm going to have u equals x squared and dv equals sine x dx. That means v is going to be negative cosine x and du is 2x dx. Okay. Use color for a different reason here. Integral of u dv equals uv minus the integral of v du. So I'm going to go ahead and say it's negative x squared cosine x minus the integral of v du. Well, it's going to be, I guess, minus the negative. Take care of that negative cosine right now, but the integral of 2x cosine x, that also requires integration by parts. Okay, so in red, I'll do this one. I'll say, all right, u equals 2x, dv equals cosine x dx. Okay, so uv minus the integral of v du, and that's okay. And so that's 2x sine x plus cosine x. And then we're going to have a plus c, but this is really just what I'm adding on here. So this is going to be negative x squared cosine x plus that plus c. I'm a little concerned. I feel like I'm missing some negativity, but I think it just has to do with the cosine derivative being negative sine. But I'll check my answer using the 3-column chart. So the first column plus minus, second column u, third column v. All right, so I had u equals x squared, 2x, and then 2. And then v was sine, no. V was negative cosine x. Scratch through that. Negative cosine x, then the antiderivative of negative cosine would be negative sine, and then an antiderivative for that would be positive cosine x. And as I multiply across, I'm going to have negative x squared cosine x, okay, check, plus 2x sine x, yep, double negative, check, plus 2 cosine x, no, I neglected that 2 there, plus c, okay, I caught an error. Okay. But again, I'm not saying you can't, but I don't know how to use this method for any situation other than u is a whole number power of x. So, if you can see ahead of time there's going to be 2 iterations, you could do this and save some time, but I don't think it's worth it in general. Okay, now x squared e to the x, That's the same story. And in fact, I do think that we did this one in quite a bit of detail. This was the one that we did in the examples in the class that showed us that sometimes this was necessary. So I'm just going to do that. If you want the full detail using what I did over here, you can just go back to the lesson. U and V, so x squared, 2x, and 2. dv is going to be e to the x dx, which does mean that v is also going to be e to the x, and all antiderivatives will also be e to the x. All right, so that's x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Okay, and so that's the first section of problems that you had to do. Antiderivatives using integration by parts. Now we're going to compute these integrals using integration by parts, and they've got bounds on them. Okay, so it's a definite integral, and we're going to still use our same formula. So for number 7, I'm going to have integral from 0 to pi of x times the sine of x with respect to x. I late algebra before trigonometry. U equals x, dv equals sine x dx. This is not one. No, this is not one we've already done. Because if it was, I'd have no shame in going up to numbers 1 through 6, grabbing that antiderivative and just using that, plugging in the bounds, subtracting. No point in doing the exact same integral twice. Wait, that would be negative cosine x. All right. Now, from 0 to pi, the integral of u dv is going to be u times v from 0 to pi minus the integral from 0 to pi of v du. Or you could just do the antiderivative yourself and then plug in the bounds and subtract. And maybe that's what I'll do and show you that that's actually equivalent in case you did it this way. All right, so my antiderivative is going to be negative x cosine x minus the antiderivative of v du. So negative x cosine x plus sine x as x runs from 0 to pi. Yeah, kind of like this. Okay, and that's going to be negative pi times cosine of pi would be negative 1, so it's negative pi times negative 1 is positive pi. Plus the sine of pi is 0. And when I plug in 0, I'd get 0 plus 0. And so that's just going to equal pi. Whoops. For 8, 3x e to the 4x. Integrating that from 0 to 1. Okay. And I late algebra before exponential. You could factor the 3 out, but I just don't think it's going to even make that big of a difference in the course of us solving this problem. So it's going to be e to the 4x dx. So then du is 3 dx. V is 1/4 e to the 4x. Got to prepare for that chain rule. So over here, the integral u dv equals u times v minus the integral of v du. I'm going to go ahead and just do the antiderivative work over here in red. So that's uv 3/4 x e to the 4x minus an antiderivative for v du. 3/4 x dx. Right. Okay, I'm going to have to divide another 4 here. Okay, and then I'd have plus c. But okay, so I'm going to be doing that from 0 to 1. So when x equals 1, I'm going to say, all right, well, this is 3/4 times 1 times e to the 4. Minus 3/16 e to the 4. And then when I plug in 0, I won't just get 0 minus 0, I'll get 0 minus 3/16. So that's, actually, I've seen multiple choice questions that look like this. So we might be wise to practice our simplifying. So that's going to be 12 over 16. Everything's going to be over 16. E to the 4 minus 3 over 16. E to the 4 plus 3 over 16. And I think this is far enough for us to go on our paper, because then we could see, 9 e to the 4 plus 3 over 16. That's going to be the right answer in multiple choice. All right, one more of these. That's going to be 9, integral from 1 to e of 5 natural log x dx. Now, if you want to just go look up the antiderivative for natural log that we figured out in the lesson, you could do that. That would be an option. Or you could just use I late, u equals log x dv equals 5 dx. That's what I'm going to do. Okay, because we can anti-differentiate 5. And then we're going to say, all right, integral of u dv equals u times v minus the integral of v du. All right, and then over here, it's going to be uv 5x log x minus the antiderivative of v du is going to be 5x times 1 over x is just 5 dx. All right, so 5x log x minus 5x plus c. So this is going to be equal to, when I plug in e, 5e natural log of e. I think to myself, what exponent do I put on e to get e? And that would be the 1 exponent. So I've got 5e times 1 minus 5e. Okay. That was unexpected. Minus the, when I plug in 1, I would get 5 natural log 1. What exponent do I put on e to get 1? That would be the 0 exponent. 5 times 1 times 0 minus 5 times 1, and that's just going to equal 5. Okay, that's interesting. All right, that's after those. Now we're going to move on to the next page. Compute the integrals using U-substitution. So the first of these is x squared e to the x cubed, and we want the inside of the composition of functions to be u. So I'm going to say u equals x to the third, so du is 3x squared dx. We don't have 3x squared dx. We actually just have 1x dx. So 1x squared dx. That's going to be a third of du. Okay. And so now, okay, that x squared and dx becomes a 1/3 and a du. I'm still integrating e to the power of something, but that something became u. Okay, but that makes our integral much simpler. So antiderivative of e to the u is e to the u. So this is 1/3 e to the x cubed plus c. I might mentally check this by taking a derivative. Okay, e to the x cubed is going to be its own derivative, and then I need to consider the chain rule. And then the chain rule, that will bring in the 3x squared. The 3 and the 1/3 will cancel. The x squared is what we need. Okay, we're ready to move on. So 11, integral from 0 to 1 of x plus 1 e to the x squared plus 2x. And so again, I'm going to let u equal the inside of the composition of functions whose derivative, or something proportional to its derivative, is appearing on the outside of multiplication. So u equals x squared plus 2x. Du is going to be 2x plus 2 dx. That's not what I've got. I just have x plus 1 dx. But how I can get that, I can just divide that by 2. Okay, and then I'm just going to use, my U-substitution to compute an antiderivative. So antiderivative of e to the power of u multiplied by half of du, that's going to be equal to 1/2 e to the x squared plus 2x as x runs from 0 to 1. Okay. Then I'm going to say, all right, this is equal to 1/2 e to the 1 plus 2 is 3 minus 1/2 e to the 0. And e to the 0 is 1, so I'm going to stop at that. Right, and on to 12, this is the integral from 0 to 10 of 8x plus 1 cubed. Oh, okay, so I mean, we could use U-substitution on this if we really felt like we needed to. I'm going to go ahead and say I can anti-differentiate this. This is going to be 1/4 of 8x plus 1 to the 4th, but then I got to think about the chain rule. So if I took the derivative of this, I'd multiply 4 over 4. That's good. Subtract 1 for the power. That's also good. But then I have to multiply by 8. Or, yeah. So I need to prepare for that by dividing by 8. And that's going to be from 0 to 10. So 1/32 of 81 to the 4. Ooh, that's a pretty big number. Minus 1/32 of 1 to the 4. And that's going to be as far as we need to go, because 81 to the 4, that's just like a massive number. And I don't think we need to do anything else with that. But if you needed to use a U substitution, you would say U equals 8x plus 1, du is 8 dx. I don't have 8 dx, I just have 1 dx. So that's going to be an 8th of du, and that's where that 8th came in. And so we'd be taking u to the 3rd times an 8th of du, so 1/32 of u to the 4th. Same thing. But if you convert your balance to u's, we saw this on the semester exam this year, if you convert your balance to u's, you got to stay in u. Don't go back to x. Right? That was the whole point of converting the balance to u. Okay, but I didn't do that on these. Maybe that'll come up later, and I'll do one like that. All right, 13. Catch this page. Number 13 is just an antiderivative of x to the 4 times the square root of 1 plus x to the 5. So I'm going to let the inside of the composition of functions be u. So u is going to equal 1 plus x to the 5. So the du is 5x to the 4 dx. I just have 1x to the 4 dx, so it's going to be 1/5 of du equals x to the 4 and dx. All right, so I'm still integrating the square root of something. It's now the square root of u, and that's going to be a 1/5 and a du. The square root is u to the 1/2 power, so I'm going to add 1 to the power, divide by the new power. So 1/5 times 2/3 u to the 3/2 plus c, and that's going to be equal to 2 over 15. U was 1 plus x to the 5 to the 3/2, add c. Next set of questions is compute the integrals using algebra. So this should be like a nice refresher, breather from the other ones. It should be pretty nice. So we're going to be, this is 14. Be integrating from 1 to 2 on x plus 2 times x minus 3 dx. Okay, we need to use FOIL. Okay, we want to use the power rule, and we can't just use power rule on each of these pieces. That was kind of the whole theme of the lesson. So first, outside and inside would be negative 3x plus 2x minus 6. Okay, 8/3, 4/2, 12. Okay, yeah. Okay, now number 15. Square root of x, so I'm just going to go ahead and preemptively write that as x to the 1/2, multiplied over 5x plus 3 dx. We need to use the distributive property. Okay, so we're going to distribute x to the 1 and 1/2. Okay, we're going to write that x to the 3/2 multiplied by 5 plus 3x to the 1/2. Okay? And then we're going to see, all right, add 1 to the power, divide by the new power, so that's multiplying by 2/5, then plus add 1 to the power, divide by the new power, that's multiplying by 2/3, and then add a plus. The integral from 0 to 1 of e to the x plus 1, e to the x minus 4. Okay, so, and kind of the theme here is on all of these, we have two things multiplied together and they're the same type. I had 2 algebraic ones there on 15. Again, 2 algebraic ones here, 2 exponential ones. And so I just need to simplify that and not use UDV. So I'm going to say, okay, we're multiplying two things with the same base and different exponents. So that's where we add the exponents. Okay. And this is something we can take the antiderivative of. You can use U-substitution if you want. U equals 2x minus 3. Du is 2 dx. Dx is half of du. However you want to do it. Either way, the antiderivative is going to be half of e to the 2x minus 3. And we're going to let x go from 0 to 1. So that's going to be half of e to the 2 minus 3 minus e to the 0 minus 3. And that's going to definitely be simplified enough for our purposes. Okay, now we've got one more. I'm just going to put this one off to the side because this one shouldn't take long either. Integral from 1 to 4 of t square root of t dt. Okay, so again, we're going to need to, kind of combine these because these are two objects multiplied together and they're both powers of t. So that's going to be integral from 1 to 4 of t to the 3/2. Okay. And we're going to add 1 to the power, divide by the new power. And that makes sense, right? This is 2/5 of 4 to the 5/2 minus 1 to the 5/2. And in free response, this is totally a safe place to stop. But, these questions are oftentimes multiple choice, so we probably need to practice simplifying our answer, and the homework's the perfect time to do that. So 4 to the 5/2, we're going to take the square root of 4, take that to the 5th power. Any power of 1 is 1. 2 to the 5 is 32, minus 1 is 31. We can double that. That's going to be 62 over 5. Okay, let's see what else we got. What do we got on this next page? Compute the integrals. Okay, with no sort of support on which technique we're going to use. Now, I'm just going to, maybe in case you were just wondering which technique to use on which, I'm going to actually put like kind of a legend over here. 18, I'm going to need to use integration by parts. I don't see anything as the derivative of something else. So I'm going to say that one's u dv. 19 is going to be u du because the derivative of x squared is 2x. And 20, that one will be u dv. And I understand that the derivative of t squared is 2t, but that's now on the inside of the composition of functions. And I definitely intentionally put that one right next to number 19, just for that, you could call it level of trickery. I would call it contrast. 21, I'm just going to try to reverse engineer the chain rule. We already did one of those. And then, I'm not seeing anything as the derivative of something else. It's kind of close. Plus, it's not going to be UDV because these are both algebraic. I'm going to need to use algebra on number 22. Okay, so that's my strategy right now. Okay, and then I've got a few more after that. This is a pretty grueling homework, but I'm only 29 minutes in, so I haven't been working too much homework this year, I guess. So 18. Integral from 0 to 2 of x e to the x over 2 dx. Okay, this one's UDV. If you want to do it the old-fashioned way, that's great. I'm going to do it slightly different. I'm going to do it with the chart, just for some variety, I think. So plus minus column, a U column, and I'll extend that a V column. Okay, I late algebra before exponential. And then, let's see, Okay, I'm going to need v. V is 1/2 e to the x over 2. Okay, so u is going to be x, du is going to be 1, so that's as far as I need to go. But there are people that do this every time. Again, I don't know how it works when u is natural log x or really anything besides x to a whole other power. But, so this is going to be 1/2 x e to the x over 2 minus 1/4 e to the x over 2 as x runs from 0 to 2. And so I'm going to say when x is 0, I'm going to have that term is 0 minus 1/4. And then when x is 2, I'm going to have 1/2 of 2 is 1 e to the 1. E to the 1. I've done something wrong here. Hold on. Okay, I was looking at this and I was like, this is a negative number, but I'm integrating a positive function, so this is bad. But I plugged in 0 first. I don't know why I would do that. It's top minus bottom. Okay, but you know what you could do is you could just kind of fix that error by saying, oh wait, that's supposed to be negative and this is supposed to be positive. Okay, and then it's all good. So let's stop there. And then number 19 is going to be the integral from 0 to the square root of pi of 2x cosine of x squared dx. All right, and this is a u du. I'll take this one all the way, even by converting the bounds. I need a different color of pen, though. I hope this one works. These pens are a little old. So u is going to equal x squared. Du is 2x dx. 1x dx is half of du. And then I need to work to convert my bounds of integration. Okay, so u equals x squared. And now it's time for me to convert my integral. Okay, so I'm still integrating the cosine. That didn't change. But the inside of the cosine is now u. And 2x dx is 1/2 of du. We're going to integrate this as u runs from 0 up to pi. And if I do it like this, I don't ever need to go back to x's. Okay, so an antiderivative for cosine is sine. Okay, sine of pi is 0. Sine of 0 is 0. So this is going to be 0 minus 0, which is 0. So I think this must have like some sort of like balanced area situation. I'm just going to make sure of that. Okay, I checked it. I graphed it and it didn't really have balanced area, but evidently the areas did balance. It wasn't obvious when I graphed it, but I did run the integral and sure enough it came back 0. So, all right, number 20. Antiderivative of t squared e to the 2t dt. I really like this one. So this one's a little tricky. I could see, student erroneously using U-substitution on that. But e to the du, that doesn't sound right, then it's not going to be right. So don't do that. This one is going to be a 2-iteration integration by parts. So I'm going to do the chart method. And I know that because u equals x squared, u equals t squared. So I'm going to have u equals t squared. I late algebra before exponential. dv equals e to the 2t dt. So that means v is 1/2 e to the 2t. Did we not just do this one? Oh, okay, no, it was similar. It was very similar. So 1/2 e to the 2t, 1/4 e to the 2t. I think I'm going to need 3. But worst case scenario, I'm just multiplying by 0. Okay, t squared, 2t and 2, I didn't need 3. All right, so I'm going to go multiply straight across plus 1/2 t squared e to the 2t minus 1/4 of 2t, so that's 1/2 of t e to the 2t, plus 2/8 e to the 2t plus c. Right. And then number 21, I'm just going to go on a new page. So for 21, I'm going to have 5x minus 6 to the 7th, and we just need an antiderivative. So, you can use U-substitution on this if you like, but I'm just going to use, kind of the chain rule and think about that. So 1/8 of 5x minus 6 to the 8th, but I would need to multiply by 5 for the chain rule if I was taking the derivative, so I'm going to divide by 5 when taking the antiderivative, and then I'll add a plus c. That's right there. And then number 22, okay, this one might be a little more involved, so I'll budget myself plenty of room. Integral from 0 to 1 of x cubed times x plus 3 squared dx. All right, now what I'm going to do is I'm going to actually multiply out x plus 3 times x plus 3 and then distribute it in the x cubed, because there's really nothing else to be done. And this one might be a little bit too much algebra for AP Calculus, but better I show you one that has too much than not give you any. So x plus 3 squared, maybe I'll just go off to the side and do a little bit of this algebra. So x plus 3 squared is going to be x squared plus 6x plus 9. And then I'm going to distribute that x cubed over it. And get x to the 5 plus 6x to the 4 plus 9x to the 3. Ooh. Numerically, this is not going to turn out great. The integral from 0 to 1, I guess at least the zero's there. So that's x to the 5, 6x to the 4, and 9x to the 3 with respect to x. Common denominator, I believe 60. You don't want to do that. We're just going to leave this one unsimplified. When I plug in 0, I'm going to get all zeros. So this is just going to be 1/6 plus 6/5 plus 9/4 minus a bunch of zeros, and we'll leave it at that. All right. I'm going to bring in the original homework sheet. There we go. Find the volume of the solid formed by rotating R around the x-axis. Ooh, it's been a while since we've done that. Okay, but I'm going to reproduce the region. Identify my radius. If I'm rotating around the x-axis, the region is touching the x-axis at all times. It'll just be one radius. It'll be a disk situation. So the radius is going to be top minus bottom. That's just f of x minus 0. And we're going to be interested in the integral of pi r squared with respect to x, rotating on the x-axis, as x goes from 0 to 1. R squared is going to be f of x squared. It's going to be square root of x e to the negative x over 2 squared. And if I multiply this thing by itself twice, I'm going to have 2 square roots of x and 2e to the negative x over 2's. So this is going to end up being pi times the integral from 0 to 1 of x e to the negative x dx. And this is going to be the type of product we need to integrate using integration by parts, meaning u and dv. So I late algebra before exponential. Let's see, u equals x, dv equals e to the negative x dx. Take derivative of u, antiderivative of v. Okay, so I'm going to think about this. I'm actually going to set up and just put my answer right here, and I'm going to do some scratch work off to the side. Switch colors. Okay, so the antiderivative of this thing is going to be uv negative x e to the negative x minus the antiderivative of v du. So negative x e to the negative x minus e to the negative x. Okay, when x equals 1, I'm going to have negative 1 e to the 1, negative 1 minus e to the 0 is 1. When x equals 0, I'm going to have 0 minus 1. So, oh man, I'm just going to copy this. Negative 1 e to the negative 1 minus a 1 minus a negative 1. This can definitely simplify. This is negative. That's not possible. Oh boy, what have I done here? I think I've got a negative number. Okay, I found it. It's right here. When I plugged in 0, that would be, or no, when I plugged in 1, that should be an e to the negative 1. So that would be minus e to the negative 1. And now that is a positive number. Have faith, we can run it through a calculator. So R is the base of a different solid. For this solid, at each y, the cross-section taken perpendicular to the y-axis is a rectangle with area given by y log y. Find the volume of the solid. This is great. This is one of those other cross-section situations. It's a rectangle, but they're telling me the area formula. So that just means I integrate y log y with respect to y as y goes from 0 to the top here. And I have doubts about whether that's 0.6. You can't see that. So we're going to say y equals f of 1. So that's the square root of 1 e to the negative 1 over 2. And that's definitely not 0.6. Quite close, but less. All right, so e to the negative 1 or 1 over e. And, okay, I'm going to go do my integration off to the side. I late log before algebra, so u equals natural log x. dv equals, natural log y. dv equals y dy. du 1 over y dy. Okay, so this is going to be 1/2 y squared log y minus the integral of v du is going to be 1/2 y di. So 1/2 y squared log y minus 1/4 of y squared plus a c, which we won't need because we're computing a definite integral here. So when I plug in 1 over e, I'm going to call that 1/2 e to the negative 2. Log of 1 over e. What exponent do I put on e to get 1 over e? That would be the negative 1 power. Minus 1/4 of y squared. Okay, that's what happened when I plugged in 1 over e. When I plug in 0, I'm going to get 0 minus. Oh! Pardon me, that was an improper integral. That shouldn't have happened. This doesn't exist because the log of 0. Okay, not possible. Oh man, I remember I was editing this problem. I guess I should have done y log of y plus 1. But this problem's really, I just want to make sure you were doing that antiderivative and setting up the right integral. If you just say minus, that does not exist, that this area, or this volume is infinite, right? Because it's going to, that natural log of y when y is going towards 0 is going to be really, really large and negative. So it doesn't really make sense. Okay, anyway. Yeah, huge mistake. But we'll survive. Hopefully, by the time you're working this homework, maybe it looks a little different. And you can come ask me how to do it with a log of y plus 1, but it wouldn't be a whole lot different. Okay, table above gives values for the function f and first two derivatives. Use the table to compute the integrals. Okay, f double prime of 3x. Anti-differentiate, that would be f prime of 3x, but we got to think about the chain rules, so I'm going to divide by 3. And so that'll be 1/3 of f prime of 6 minus f prime of 0. So that's 48 over 3. That's 16. That's nice. Okay, x f double prime of x dx. This one will require integration by parts. So I'm going to say, all right, u is going to be x because I don't want to take the derivative of f double prime. I don't have a row for f triple prime. That'll be helpful. F double prime of x dx equals dv, so that means that v is going to be f prime of x. Okay, I'm going to copy in the formula. The integral of u dv equals u times v minus the integral of v du. And so that's going to be equal to uv is x f prime of x minus the integral of f prime of x dx. It's going to be f. There you go. Okay, I'm going to go over here and say, all right, x f prime of x, 2 times f prime of 2 minus f of 2 minus 0 f prime of 0, this is going to be 0, minus f of 0. Okay, so negative 12 plus 2 is negative 10, plus 6 is negative 4. 27. F prime of x times f double prime of x. Now, if you want to try this with UDV, I don't know what's going to happen. I'll be totally honest with you. No, you would have to know something about the integral of f prime of x squared, I think, if you let dv equal f double prime. So this one's actually UDU because the derivative of this thing is appearing on the outside with multiplication. And I don't know if we've done one like this yet this year, but u equals f prime of x du equals f double prime of x dx. I'm going to actually just convert the bounds also. So I'm going to have basically x equals 0 gives me u equals f prime of 0, which is 2. And then when x equals 1, u equals f prime of 1, which is going to be negative 5. Okay, so now I am integrating from u equals 2 to u equals negative 5 on u du. So it's 1/2 u squared. All right, so that's 1/2 of 25. What? That's 1/2 of 4. Make sure of that. Okay, wow, I really got myself confused on that one. So, wait. Okay, yeah. So I was like, okay, this is a positive number, but I'm expecting it to be negative because, from negative 5 to 2, like I've got more negative area than positive area, but I'm integrating backwards. So it's like kind of a double negative situation there. Hopefully you didn't think about that too hard. E to the f of x times f prime of x, this is going to be another u to u. So u is going to be equal to f of x. Du is f prime of x dx. And that will be 1 to 6. X equals 1. That gives me u equals f of 1 was 4. X equals 6. U is going to be f of 6, which was 54. So I'm integrating from 4 to 54 on e to the u du. And that's its own antiderivative. So e to the u from 4 to 54. That's e to the 54 minus e to the 4, which is a massive number. Okay. Then it is known that the integral from 0 to 6 of f is 36 with the integral of x times f prime. Okay, so that's going to be u equals x dv equals f prime of x dx. I don't see anybody's derivative hanging out anywhere. U equals f prime of x dx, and so that means v is f of x and du is dx. Okay, so the integral from 0 to 6 of x f prime of x dx is going to be x f of x from 0 to 6 minus the integral from 0 to 6 of f of x dx, which they told me is 36. All right, so 6f of 6. And f of 6 is 54. Okay, that's kind of a lot. Minus 0 f of 0 minus 36. I'm going to stop there because that arithmetic is kind of a lot. That would be, 324 minus 36. arithmetic errors waiting to happen if I do that. So I'm just going to stop there. Okay, so suppose g of x is a function with g of 1 equals 3, g of 6 equals 13, and g prime is always equal to 2. What is this integral? This one's kind of new to me. I'm not familiar with this one. So, but I saw one like it elsewhere, so I thought you might be needing to see it. So g times f double prime. I'm going to definitely let u equal g of x and dv equal f double prime of x. Okay, that means that v is f prime of x and du is g prime of x dx. Okay. And so integral of u dv from 1 to 6 is going to equal u times v from 0 to 6 minus the integral of v du. Okay, and then they said g prime of x equals 2 for all x, so I should probably do that. V is f prime of x, du is 2 dx, and we're going to be integrating that from 0 to 6. All right, so g f prime at 6, g times f prime. G is 13, f prime is 50. That's another big number. Minus g of 0 is 3, f prime of 0 is 2, and then minus, wait, remember your parentheses here. Okay, 2f of 6, that's 108, minus 2f of 0, it's 12. I might have done this one wrong this morning. But that's only a numerical error or a table lookup. I mean, I just made one right here. That's our answer. We could simplify this, but the numbers are kind of a lot, so I think we're best off stopping there. And that's all for this homework set, so that's all for this video. Thanks for watching.